For the longest time I thought it was Huffman, like Matt, but I just can't listen. I'm dyslexic, so sorry. I have an outline this time. What is it? How does it work? What is it good for? Any questions so far? No? Okay, so what is it? It's a lossless expression algorithm utilizing variable length codes. How does it work? A really interesting part. You create a node for each character. Like, it doesn't actually have to be a character, but let's just go with that. Label each node with a frequency, so like how often it occurs, right? And then you arrange it in ascending order of frequency. So like, goes up, right? You join the two lowest frequencies together in like a graph tree-like thingy. Then you repeat steps 3 and 4 until there's nothing left. Then you join it all together and you get a compressed string. So, I took the beautiful sentence of life adaptation is good, and like literally on the last slide I found out I made a mistake. So life adaptation is not good, it's good.
Oh no.
So yeah, I thought I would leave that in because I forgot the D and it turned into good, never mind. Anyhow, you split it up, write all the characters into single nodes and give them their frequency. So you see there's like the actual character and frequency, should be pretty self-explanatory. This is a space, right? Because spaces matter. And then you join it together, like this, and you get the combined frequency on top. You rearrange, and very quickly you find out you don't have enough space. Keep going, right? So you keep doing it, you rearrange, right? All this stays the same. And then we skip a few steps because there was no space. I tried. And yeah, you keep joining them together, right? At the ones with 2, you keep arranging them, then you join the 2 together, you get 4, and all that, right? And you get a beautiful, beautiful Huffman tree. Good. Then you label left and right with 1 or 0. It doesn't actually matter which one you choose. Just, be consistent. You will just invert the code. And then you traverse through it and assign the values to the characters, right? You get something like that. To give you a little example, if you try to find the dot is there, right? Start at the top and you try to find it. So you go 1, 1, 0, 0, 0, 1, 1, 0, 0, 0. Worth noting that the most frequent character, the most used character, thereby gets one of the, gets the shortest, right? So the one you use often gets short. And then you join it all together in like one long string. And like if a letter repeats, right, you just take your good old word, like life adaptation, visit, life, start with that, and you attach the I, you keep going, right? Literally, when I was there, I found out I didn't have to deal with it, so that. And yeah, there's your encoded Huffman string. Nice. To get it back,
I'm just giving you 2 minutes.
Yeah, and like to decode it, you do the same backwards. Who would have thought? But what is it good for?
That's a good question.
It saves a lot of space. As in, it's actually, if we go to Google Tree, it is basically, it is like mathematical optimal. It is the best distribution you can get if you choose like single letters. For example, this one is 77 bits long. The original string was like 157, I think. So in this case, you actually save like 50%. Usually the more longer the text is, the more you will save, which is always a bonus. The problem is you need to store the tree as like a little key, right? Because you could arrange this differently, right? Like this bit could be over there, this one over like here. Doesn't matter, you just need to follow it through, right? And yeah, that is what it's good for. That's why it's cool. It's optimal, right? Fun story. Why I actually wanted to do this. The guy Huffman, right? He did this for his doctor thesis, and his professor was the guy who did the previous version of this, where he started the other way around and just made like an evenly distributed tree. and him and Huffman didn't get along so well, so he was kind of just, okay, I dare you. And then Huffman came along and wrote the best version of it. Ooh. And what else? Oh yeah, you don't have to use letters. You can use like words. Makes it a little more efficient, but it's a little more complicated. And I thought this was just a beautiful little thing.
Cool.
Nice. Yeah. I said.
Yeah, so is the benefit just that instead of taking a normal binary representation of a character, that you are enabling
Oh yeah.
shorter representation by way of frequency?
Very good question. Oh yeah. Like in this case, the character is like 5 bits long. I think normal ASCII characters are 7, right? So you already save something from 2 to like 5. So generally it's just shorter.
Yeah.
Good thing.
Cool.
I didn't get the decoding part where like you get that long sequence here. How do you split it? So like for example, this one has 0 and 1, the first one has 5, like 1 1 0 0 0.
Yeah.
So how do you know how to split that sequence?
They don't repeat, right? As far as I think, as far as I remember.
But like a space and then a capital A looks like the same at the end.
Is it? Yeah.
There's no 111.
Oh yeah, the only time there's 3 ones.
The codes are all unique from.
Yeah, because they can't be duplicates, right? Because there's only like you only count the what's called the leaves.
Yeah.
So you can't actually get a duplicate. That's the beauty of it. Probably a good part to mention. But it's optimal, right? It can't really be improved upon. Which is, oh yeah, side note, a JPEG compression, right? This whole, I guess the whole thing of this, that you don't get repeats, you store them in it. Actually, hold on a side note, never mind.
No, it's good. Thanks for this. This is a nice follow-on from your last one.
Yeah. Oh yeah, there's I think part of something called Huffman notation for it, where like if the end is just zeros, because nothing repeats, you can like you know what it is and you can just drop them. I think you write like some special mathematical notation for it, which is like in this case you would save a whole 3 bits. And yeah.
Nice.
Thanks. Thanks.
Since the Wi-Fi password, huh?